So now let's talk about comparison between both reaction SN1 and SN2 as we have seen previously. So we know in case of SN2 reaction and SN1 reaction comparing, first the point is that SN2 is an elementary reaction. It is a single step, so we know single step is elementary reaction. There is no mechanism or no intermediate or no mechanism involved. Okay, so here we don't have any mechanism in first step, so it is an elementary reaction. It's a single step reaction. And SN1 is a complex reaction. It may proceed in multiple step reaction. So as we see, SN2 is considered as a one step reaction, and SN1 is considered as a multi-step reaction. So now even if we talk about the rate, so rate is directly proportional to the concentration of nucleophile and concentration of alkyl halide here. Now in case of SN1, the rate is only directly proportional to the concentration of alkyl halide. It is independent to the concentration of nucleophile. So as we know that order and molecularity both are 2 in case of SN2. In case of SN1, order and molecularity is equals to 1. So we know there is no rearrangement in case of SN2. It is directly in formation of transition state, then it directly forms the product. Now if we talk about rearrangement of carbocation, so in SN1 there is a rearrangement of carbocation. If we talk about SN2, we have seen which is both stereoselective and stereospecific, but in case of SN1 it is stereoselective. It is the selected towards the formation, the reactant is selected and giving a particular reactant is giving a configuration, but it is the not stereospecific. The product are not stereospecific. Polar aprotic solvent favors SN2. So we know polar aprotic solvent, so solvent which do not have the positive tail, a free positive tail. So it surrounds the, so it repels the nucleophile. So when it repels the nucleophile, so the intensity of nucleophile increase. As the intensity of nucleophile increase, so it considered as a both 2 degree. So the substrate and reactant both are considered as considerable amount, or we know concentration is considerable, so order is 2 there. But polar protic solvent, the solvent which have protic tail, okay, like H+, so in that case both the positive charge and negative charge both will surround, okay, positive charge and negative, the portion of that alkyl halide both are surrounded, so that considered as a SN1 step. So here we know that they got separate and it may rearrange. So polar protic solvent favors SN1. Now if you see further the common point, the leaving group has same effect on SN1 and SN2, because RDS of both reaction involve carbon leaving group or bond cleavage. So we know what are the common between SN1 and SN2. We know between SN1 and SN2 both are substitution nucleophilic. So leaving group or alkyl halide has same effect on SN1 and SN2, and it decide whether it is SN1, and in SN1 how fast is the rate. If we talk about SN2, now in SN2 how fast is the rate, that decides the leaving group. So if we have a same alkyl halide, the alkyl group is same and we have different halide, so we are talking about the alkyl halide here, so which have a leaving group. So whether it is SN1 or it is SN2. So if we talk about their leaving group tendency, so we know more the acid character, if it leaves the I minus, so I minus formed by the acid HA, so HI. So HI here is a very good acid as we compare between bromine, chlorine and iodine. So more good acid, okay, good acid means it is a good leaving group, directly proportional to good leaving group. So here the rate will be higher in case of iodide, and then bromide, and then chloride, and then fluoride. So now if we talk about the log of rate versus Now, if you log of rate versus different degree of alkyl halide, this is methyl, this is 1 degree, this is 2 degree, and this is 3 degree. Now we have to see if this is given and nucleophile is given, then our base is given, then how could we predict whether the reaction will proceed through SN1 or SN2 mechanism. So if we see, if we have methyl bromide, if we have 1 degree bromide, then it surely will be SN2. Here it will be SN2 mechanism. But if we talk about the 2 degree, in case of 2 degree alkyl halide, there could be SN1 or SN2. Okay, let's leave it this for now. Okay, let's hold this. So now if this 3 degree, it will surely go towards SN1, because we know nucleophile has a lot of crowding here, so it cannot proceed through SN2 mechanism. Either it will go elimination, but it will not proceed through SN1 mechanism. So when it is 2 degree, then how we will decide whether it is going through SN2 or SN1? So now if you see here, now here if you see that when it is 2 degree, it is 2 degree alkyl halide. Again it is, now we have 2 cases. One is when the nucleophilicity is less, okay, and the nucleophilicity is more. So we know nucleophilicity more in case of negative charges are more nucleophile considered as a lone pair having. Okay, if element having lone pair and negative charge, we know negative charge will be a good nucleophile. So if we talk about here now we know that and now if we have water here as a nucleophile. Okay, if we talk about the solvent, here we have polar protic solvent. As we have seen previously in case of SN1, there should be a polar protic solvent. When it is polar protic solvent, or we can say weak nucleophile, now if we have to see the solvent condition is important. So we see here at the polar protic solvent, so it is polar solvent and it is protic, so it is favoring towards SN1. Now it is favoring towards SN1. Now we will get 2 types of product here. Okay, now but if we talk about, like if we take an example of CH3 minus, one more acid if we take, okay, now in that case if that product will be CH3. So here if we have high intensity of nucleophile, or we have polar aprotic solvent or high intensity of nucleophile, then it surely will that favoring towards SN2. Here it is a inversion in configuration. So that is the difference, that how we will decide whether it is going through SN2 or SN1. Now let's see if we have a reactant and we have to decide whether it is going from SN1 or SN2. So if we have benzyl chloride, okay, in case of benzyl chloride, it is chlorobenzene. So in case of chlorobenzene, we know there is that resonance, it is stabilized by resonance. So it is a resonance stabilized, okay, it is a resonance stabilized halide or nucleophile or living group. So it will not leave that benzene ring. So in case of chlorobenzene, neither it will show SN1 nor it will show SN2. So again, if you see here, chlorine is again involved in resonance here. So it will neither will go by SN1 nor will go by SN2. Again, a resonance stabilized by allylic group. Okay, this particular group is known as allyl. Okay, so it is allylic resonance. Okay, now if we see RF, so we know in case of this will not even go by SN1 and SN2. We know when living group favors have a common area between SN1 and SN2, the consideration is common between SN1 and SN2. So when it is a poor living group, it will not follow the substitution of nucleophile. So it will not go, because it is a very poor living group. Now if we talk about the structure, tertiary chloride, okay, here we have, so we know it will not go towards SN1, not towards SN2. So we have given this notorious carbocation. Okay, this is notorious towards SN1, because we know here it could be it neither can be SN2 or neither SN1 nor could be SN2, because in case of SN2 we are seeing here it's a crowding in case of SN2. But if we talk about SN1, so we know that carbocation is 1 degree. Carbocation is 1 degree in case of SN1. So it will not be following SN2 nor be following SN1. Now this is a little bit different. So now if you talk about bicycloring, in case of bicycloring, we know it will not go towards SN1 or not towards SN2. Why? Because it Brett's rule violation. There will be a Brett's rule violation. So now if you see SN1 mechanism, so it will be, in case of SN1 mechanism, it will be leaving and it will be forming sp2. Now we know, according to Brett's rule, this bridgehead carbon can never get the configuration of sp2. It can never be the planar. So it won't follow SN1, and it will also not follow SN2, because in case of SN2 it will having either transition state, the planar transition state, and it cannot form a planar structure. Now if we talk about this particular 2-degree alkyl halide, so it can either form SN1, it can either go by SN2. Okay, so if we have good stabilize, so we know where it will be a good nucleophile. So when we will consider good nucleophile, in case of good nucleophile it will be SN2, and in case of 2-degree stable carbocation, when carbocation 2 degrees stable, then it will be SN1. So it can favor both SN1 and SN2. If we talk about next structure, this will also again favor SN1 and SN2. Same is the reason. When there will be a good nucleophile, then we will go towards SN2. When the carbocation will be stable or polar, when polar protic, then it will go towards SN1. Now if we consider this 3-degree halide, we know that 3-degree halide never gonna see the SN2 reaction, but it will favor the SN1 reaction because it is 3-degree halide. 3-degree halide and it is stable. So 3-degree halide is stable. So it will never form toward SN2. It will not go on SN2. And here 3-degree halide. Okay, now it is stable carbocation. Due to stable 3-degree carbocation, it will go towards SN1 mechanism. Now we talk about methyl chloride. We know methyl chloride will never go towards SN1, but it will form towards SN2. Why? Because we know that it has unstable carbocation. Why it is not going towards SN2? Because SN1, because it has unstable carbocation. We talk about CH3 plus carbocation, which is very unstable as we compare to 2-degree, 3-degree, and all. So now if we talk about benzyl chloride, in case of this benzyl chloride, it will go toward both SN1 and SN2, because in case of good nucleophile it will form SN2 mechanism, but in case of stable carbocation it will form SN1 mechanism. So if we talk about this next structure, that in this structure it will not go towards SN2, it will not go towards SN2, but it will form SN1, because again 3-degree halide is stable. It is 3-degree halide, so 3-degree halide will surely will favor SN1 only, so 3-degree halide, so that's why it is not SN2. And stable 3-degree carbocation, that's why it is SN1. Now we talk about next structure. This will neither go SN2 nor go SN1. Again, this is resonance stabilized. Again, it is a resonance stabilized. We know when it is a resonance stabilized, which kind of resonance is there, which kind of group is there. It is a vinyl halide. Vinyl halide. So when our double bond is in directly conjugation with that compound having lone pair, or when this type of resonance is there, this type of group is known as a vinyl group. So it is resonance stabilized. It is due to vinyl halide. Now we talk about this reaction. We know this reaction is a stable carbocation. So when it's stable, again if we see this compound, so here it will not go towards SN1. It will go towards SN2. It will go towards SN2, but it will not go to. And this is a little bit strange. Okay, this particular compound, if we talk about, then alpha halo keto is most reactive towards SN2. Is most reactive towards SN2. So it is a little bit not according to trend. According to trend, we are not considering here the steric crowd or the stability of carbocation. So in case of alpha haloketo, okay, it is alpha, okay, it is halogen, okay, when we have halogen on alpha, okay, when it is a ketone group, so it is most reactive towards SN2. So again this is a little bit different, and this is also a little bit different.